Let's look at some relays. What we have in front of us are 4 relays that you would find in either a commercial transport or automotive application. These ones, probably more commonly, these small format ones, more commonly found in the automotive application. These ones really commonly found in commercial transport and mobile equipment. If you buy a relay base that can be installed after the fact, very common, they have this style, this bigger format. So what we can see really quick is that we have 2 different styles even of these small and the large. And it's as simple as seeing 1, 2, 3, 4, 5 pin versus a 4-pin relay. So this is our 4-pin. You can see that the 5th leg of that relay has been manufactured missing. And we see the 5-pin relay right there. All the pins are intact. And that's true for the small format as well as the large. Now, what's the difference? Well, I'm going to use these 2 schematics that are written on the side, and these are especially helpful. And almost all of our relays have their schematic drawn on the side. These are a DIN schematic, so it's a German numbering system. Each of the numbers, 30, 87, 85, 86, all correspond to an industry standard system. So 30 is connect to battery positive, 86 is supply to coil, 85, I believe, is switch coil. 87 is switch load. All of those are part of the DIN numbering system. So if you're wondering where that number system comes from, it's the DIN German numbering system. Anyway, what we can see in our 4-pin relays on both of these, and I'm going to pull up my 5-pin relay on this one to show the difference. So maybe I should just hold these 2 for now. If we compare the differences, we can see on the 4-pin relay we have a 30, which is supposed to, or most commonly runs to battery positive or voltage supply, let's call it that. So it's going to come in 30, and it comes to this switch, and this switch is normally open. See how it's not drawn connected? So that means 30 to 87, there's no continuity yet. Now, 85 and 86, those are what we would call the control circuit. We can send power in on 86. It goes through our coil. So this is our magnetic coil. And it's going to go through 85 to ground. And when the magnetic field is created, that switch closes, and now we get continuity from 30 to 87. The reason for this, a lot of our relays have about 70 to 100 ohms of resistance. So they have very low current. They're somewhere in that 3 amp range to control a relay. So now we can have 3 amps control. Some of these can be rated all the way up to 40 amps. So you can have 3 amps control 40 amp loads. And that allows you to use small switches to control large loads. So this has been the 4-pin relay, looking at 1, 2, 3, 4 pins, 2 of them being the control and 2 of them being the load circuit. What about a 5-pin relay? Well, a 5-pin relay still has a 30 terminal right here. That 30 terminal has a normally closed and a normally open position. So the normally closed goes to 87A. So this switch assembly right here is a single pole double throw within the relay, and it is acting like an electrical diverter valve. So it's either going to send voltage potential to this terminal or to this terminal, but there isn't a world where there isn't a terminal charged, like on this side. So this guy either is charged to 87A or to 87. Now, you can still choose to wire this as a simple on-off. You just don't hook anything up to 87A. But in the same way as the 4-pin worked, the 5-pin operates where we will send power into 86 through a switch, goes through the coil, goes through 85 to ground. The coil gets energized, the magnetic field pulls the switch over, and 30 to 87 are now connected. So now we are moving our load current to our device. When we disconnect our switch that was in 86 and we de-energize this coil, one thing you'll notice is this drawing of the box right here or the resistor right here. This is what's called a clamping diode or a clamping resistor. The reason for that is every magnetic field that is created through electricity, when it is de-energized, it collapses significantly faster than it was created. And when it collapses at that high rate, the voltage goes up. That voltage can create an arcing at our switch, and that can damage our switch. So on small switches like this, without the clamping diode, very quickly we would arc them out, and they would eventually have a high resistance in the control, which those resistances add to the resistance of the coil, and eventually the relay will be so weak that it will not actually be able to operate the switch. So that's important. And so we need to protect it. So you can find relays like this one in the world that are lower price, and they have 85 and 86, 30 and 87. This is a 4-pin, but there is no clamping diode here. And it's simply just a quality thing. So we have a clamping diode to protect the switch, which is especially good in electronically controlled switches and small toggle switches that can wear out and arc out. Well, let's take a look at what's inside of a relay. And what I'm going to do is use this 5-pin diagram on the side of this relay to work with this one, because this one's hard to read. It's not been painted over. These relays are quite easy to open. Generally, you can get in behind them and pop them. Of course, I prepped this one, and it's possible that you can damage them, so then it makes it even easier, but it makes it harder to put them back into service. But for teaching, it's fine. All right, so we're going to use this exploded view of our relay, this opened up unit, and we are going to ID all of the components in the schematic on this unit. So let's start first with the control coil. 86 goes into a control coil, goes to 85. This red coil of wire is our control coil. So it is energized through pins 85 and 86, which are labeled on the bottom of our relay, so this one and this one. And so when we look at this, we can see that little tin plate right here. And that tin plate has a very tiny silver red wire right down in there, hard to see, that makes connection. This is one conductor wrapped around this coil many times. Now it's resin coated wire, and that prevents the short circuiting of the coil. If you had a short circuited coil, the current in the coil would go up, but the power of the coil would go down. And that could make it not work strong enough to pull this switch over into its right contacts. So the other side of our 85 and 86 is right here, and that's also connecting. One of the things we can see is this little blue odd shape right here, and that is our clamping diode. So hard to tell without reading the band colors whether that's a diode or a resistor, and you can read the colors and that would tell you. You could also use your multimeter and check it with a diode function or a resistance function. But that is our clamping diode that's used to dissipate the induced voltage from this coil when the 85 and 86 is no longer powered. So that's what that diagram represented. So this little clamping diode, let's look on the diagram right here. That little block is that little blue thing right there. Now, one thing that we don't normally see, and we can't see in the diagram, other than the fact that 30 goes to 87A normally, that's its normal condition, is this spring right here. This spring is what's giving it its normal condition. If I removed this spring, some of you have heard this before when you pull a relay, and that's the rattling noise that comes when the spring has failed. So if the spring has popped off, then what happens is the relay will rattle. So if you pull it and shake it and it rattles, the spring has popped. You can either try and pull the relay apart and put it back together, or simply replace the relay. Alternatively, what could have happened is the spring let go and our actual electrical contactors, so we can see it's going up and down, has popped out of the pivot plate right there. And so now it's just rattling around, and likely we should just replace that relay. Now, I want to take a look at the 87A and 87. We did 85, 86, the coil, we did the clamping diode. Now let's look at 87A and 87. That is two electrical contacts. So there's one right there. So that's the normal position. That's the one it's in contact with. So that would make it 87A. And then we see the electrical contact on the other side right here, and that would make it 87. And if I pull it over, we can see that the lever that's in the middle moves from one position to the other. It's spring-loaded to 87A. When the magnetic field of the coil is energized, boom, we pull over and now we're electrically connected to 87. But where does the source come in? Well, that's right here. This big plate goes all the way down through and into our 30 pin, which is right here. So the 30 pin is where our voltage supply is going to come in. This braided copper wire comes over to our electrical plate, and that's what's making the contact to our 87A and 87. So that's all the components of our relay: our coil, our clamping diode, the normal spring, the supply from the 30 to our lever, our electrical connectors of 87 and 87A. And the reason why that's good for us to know is we got to talk about how these fail. And how they fail is typically these connectors right here, the buttons can actually wear right off. They can pop off, which make them a highly resistive connector. So even though your coil's working, you have a high resistance from 30 to 87. So that's a possibility. And you would see that by energizing 85 and 86, even with a Milwaukee battery jumper. Buy a battery pack and you can jumper the 85 and 86, or just use your battery or a 9-volt battery and some alligator clips, and you can jump this, and usually it'll energize and close that connector, and then you would read your resistance from 30 to 87. And if it was an arced out terminal, you would see a high resistance from 30 to 87. Normally, with 85 and 86 energized, 30 to 87 should have 0.1 ohms of resistance, essentially none. So the 0 on your meter. When you have 85 and 86 de-energized, 30 to 87 should be reading at 0. And so that's the either or of a 5-pin relay. If you check continuity, or your resistance value really, between 85 and 86, every relay is going to be slightly different. But most common for these ones that we've looked at, a common number is between 70 and 100 ohms of resistance between these terminals, although you will need to check the spec sheet on your relay. If you read OL from 85 to 86, that's the control coil. If you read OL, that's out of limits, that's an open, that means the coil or the connector has failed and the relay needs to be replaced. If you read low, like 5 or 10 ohms of resistance from 85 to 86, that is an internal short in the terminals from one side to the other, and the coil is not operating. And what will happen is you will always stay in the 30 to 87A position. You will never get to the switched position. And so your relay, again, needs to be replaced. Being familiar with these relays, the build, and the terminals allows us to be able to diagnose them. Whether it's a 5-pin relay or a 4-pin relay, the operation of this relay is exactly the same. So you're checking for resistance from 85 to 86. You're checking, if you power 85 and 86, the resistance between 30 and 87. And energized, this should be 0. De-energized, this should be OL. De-energized, 85 to 86, should be somewhere 70 to 100 ohms. We don't check ohms energized, so we'll just pause it at that point. All right, hopefully this has been helpful for you to understand what's going on with your relays. And that's true for this one, they're all the same. Now, all of us know this trick, and we're aware of it. The cheap way to diagnose a relay is to simply have another one. And if you think the relay is the problem, have another one. They're fairly inexpensive. And instead of needing to go through the large process, it's not even that big, but instead of going through the process of actually testing the relay, if you have a spare, you can simply pull it, replace it, make sure the terminals are the same, the pinout is the same, and make sure you're replacing a 4 with a 4 and a 5 with a 5. And it is good for you to make sure at least the amperage rating of the relay is good, so you're not causing the failure of the relay after you install it. But otherwise, jumping same part number to same part number, even within a fuse box of 2 different devices, can be a very quick way for you to diagnose, well, I swapped the relay and now it works, put them back, now it doesn't work, replace the relay and move on. So while we know how electrically it works, those are helpful when we don't have spares. When we have spares, sometimes it's just easier to do a swap and test.